Hello everyone, welcome to 8.2, Law of Sines and Law of Cosines. So today we are going to define the equations for sine and cosine law and determine when it is appropriate to use them, and then we are going to use sine and cosine law to solve problems. So let's start by talking about what sine and cosine law even are. So when we conceptualize the idea of a triangle, right, the idea is that we have three angles and then we have three sides. Well, what's true about a triangle is that the larger the angle, in other words, if we look at angle A here, the larger angle A is, the larger the opposite side length will be. In other words, if angle A is the largest angle, side A will be the largest side, right? So when we're using sine and cosine law, that's kind of how we talk about our angles and sides, is we think of them in terms of a relationship. So in other words, if we're looking at A, we care about the relationship between angle A and the opposite side, which we will call small a, right? And that's what we're going to use for all of these things. So we'll call all of our angles the capital letters, and then we'll call all of the opposite sides the same lowercase letter. Okay, and that's what we're going to use for our formulas. Now, like I said before, the relationship between the angle and the side is important. So when we look at law of sines, you'll notice that that's what this is. These are just a bunch of ratios, and we won't need all three of these, right? We'll only ever need two. But the idea is that it's always true, right? If I take the sine of A divided by the side length of little a, that's going to be the same as the sine of B over little b, right? The ratios are the same. We can set up a proportion using those ratios, and that's what law of sine tells us. Now, law of cosines is a little bit more, I guess it's a little bit more involved, if you want to call it that, because we get to pick, right? With law of sines, we just plug in what we have, right? With law of cosines, we're going to be able to pick which one we need and rearrange this formula a little bit based on what we're solving for, right? So you know in Pythagorean theorem, you can essentially rearrange it. I'm just going to write this here real quick just to kind of show you. We can rearrange it if we're finding a side, right? We can rearrange this as like c squared minus a squared, right? And if we're finding our hypotenuse, we can just do it as the square root of a squared plus b squared, right? We can kind of rearrange our formulas to use what we need. Think about with law of cosines, that's kind of the idea of what we're doing. Like, depending on what we're solving for, we're going to change the formula around just a little bit. And it's not even that we're going to move, like, this is going to be the basic form of it, but we get to choose what A is and what the cosine of our angle are based on the thing that we need, right? So the only thing that's really important about this is whatever side we choose to be out here by itself, right? You'll see how this side equals everything else over here. We get to choose whatever this side is, right? But it's important that the cosine of the angle here, everything else here is a side, right? The only angle is here is this cosine of A. You notice that the A matches the side that's out here, right? And that's really the only important thing. It's the side we're looking for, right? The cosine of that angle, and then everything else on the inside here, on the other side, those are just the side lengths of the side that we don't choose, right? And we'll do an example of this, but I just wanted to kind of let you know, we could choose, if we wanted to make this lowercase b, and then this the cosine of capital B, and then switch out these b's for a's, we could do that, right? We can pick which one we want. So it kind of works, like I said, the same way as we did Pythagorean theorem before. So all right, so when do we know, when are we supposed to use these, right? Well, let's think back to triangle congruence that you did in geometry. So let's think about what we had. So we had a bunch of different ways that we could prove that triangles were congruent, right? For instance, we had angle, side, angle, which is where the side was kind of smashed in between the angles. So we had an angle, a side, and then an angle. We had angle, angle, side, which is where we had two angles and then a side afterward that wasn't in between, right? We're going to skip this for a second because this one doesn't exist. And then we have side, angle, side, which is where the angle is smashed in between the sides. And then we have side, 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 okay? Now, there's one more. It works similarly. This is not a way to prove congruency of triangles, but it will work for our situation here, right? And it's called side, side, angle, right? In other words, we have the two sides here, and then we have an angle, right? One way that's easy to remember this is if you spell this backwards, it gives us a bad word, right? And that bad word is going to give us trouble in the future. We're going to have to actually do a few extra steps with this. So if that helps you remember it, that's how I help. Like, this one is like a naughty triangle, and we have to use stuff to make it work out. So, All right, so here's a quick summary of when to use them. Essentially, when we know two of the angles, we're going to be able to use law of sines, right? And when we know two sides, we're going to be able to use law of cosines. The only difference is this one here. This one kind of breaks our rule. This one we're going to use law of sines, but we're going to have to do a little bit more with it in order to determine if there's 0 answers or 0 possible triangles, 1 possible triangle, or even 2 possible triangles with the information they give us. So we're going to have to mess around a little bit more with that, and we'll go over that here in a second. But this is the special one out, right? Other than that, if we have 2 angles, it's law of sines. If we have 2 sides, it's law of cosines. And you'll see that if you tried to plug these into the formula, they just wouldn't work, right? So, okay, let's give it a shot. So let's start off by using sine law for angle, side angle, and angle, angle, side. So if this is our problem here, and this is the information they give us, they're asking us to find z, which is this side over here, right? Not angle z. We're finding the side length of z. Okay, so if we're trying to find z here, well, first of all, what do we know? Well, it looks like we have a side, and then an angle, and then an angle, right? So we have angle, angle, side, right? So which is this here. So we're good. We can use sine law for this. So when we set up sine law, remember that it's the sine of the angle. In other words, we're going to start with x. So the sine of 32 divided by 1,000 is going to equal the sine of 39.8 divided by z, because this is the one we don't know, right? So in other words, angle x over side x equals angle z over side z, right? So let's do that. So let's plug it in. So we know that we have the sine of 32 degrees over 1,000, right? Because that's the corresponding side here. And then we know we have the sine of 39.8 divided by our side, which is the one we don't know, which is z, okay? Now, all we have to do now is algebra. The first step in any kind of problem like this is we're going to cross multiply, right? So we're going to take this and multiply it by this, and we're going to take this and multiply it by this, right? Hopefully you guys remember this concept when we do proportions. And from there, you're just going to solve. If you want to pause the video and try and solve it, I would strongly recommend do that to practice your algebra with these trigonometric functions here. Go and pause the video and see if you get 1,207.9, and then we'll come back and I'll kind of briefly explain what I did. All right, so we cross multiplied, right? Which means we have z times sine of 32 equals 1,000 times sine of 39.8. So this all equals each other. Now, in order to find z, we have to divide both sides by sine of 32. So I divided both sides by sine of 32 here and here. And now we just have this whole piece here, which is just a number, right? So first I evaluated in my calculator, I evaluated the top, and then I just took that number and divided it by sine of 32, and I got 1,207.9. Easy enough, that's it. That's law of sines, right? It's not super complicated. It's the most complicated part is plugging it in and just making sure that you're doing the algebra correctly, right? But once you get a hang of that, it's really not too bad. And you can do these problems usually pretty quickly. All right, so using sine law for side, side, angle, and solving for ambiguities. Now, there is the potential in these problems that these could have 0 sides, or 0 triangles possible, right? And basically, the only thing you need to do that is, I don't know if you remember from Pythagorean theorem and converse, it was the idea that when we have a triangle, right, if we have, let's say we have 3 sides here, right, our longest side, this one here, we'll call this C, and then A and B. In order for a triangle to exist, A plus B has to be greater than C, right? Otherwise, the triangle can't exist. So we could do the same thing here, right? We could find this side length here, and then determine whether or not it's actually a triangle to begin with, right? I'm just going to tell you for this problem that it is a triangle. It's actually going to be 2 triangles, right? But just so you understand, like that is a possibility, right? They could try to be tripping you up with this, but that's technically true for every triangle, right? Not just for this ambiguity situation. Okay, so remember, we're doing this for side angle, right? Look at it backwards, right? It's bad, so we have to make sure that we check it. Okay. So we have triangle CDE here, and we know this is we don't actually know this piece yet technically. Okay, we're trying to find it. So just pretend like you didn't see that. All right, so we're trying to find angle E, right? So we know that we have an angle of 30. We know that we have a side opposite that of 6. And then we know we have the side opposite angle E is 8, right? And we're trying to solve for E. So go ahead, if you want to pause the video now, I'll actually scroll up to not give you the answer. Go ahead and pause the video now and see if you can solve it and see if you can get 42 degrees. You should get 42 degrees, okay? All right, so let's just go over it real quick. All right, I did the math kind of quickly, but I can kind of walk you through this a little bit. This involves taking the inverse sine, so hopefully you got this. If not, no big deal. So we set this up as sine of 30 over 6, right, equals sine of e, because we didn't know this at the time, over 8, right? And then what we're going to do is cross multiply, so we'll get 8 times sine of 30 equals 6 sine of e. And then because we have 6 sine of e and we're trying to solve for e, we're going to have to divide by 6. So I kind of did this in one step, but we'll have 8 times sine of 30 over 6 equals the sine of e. And now, well, we still need to get the sine of e, or we still need to get e by itself. So to get rid of the sine, we take the inverse sine. So here we're going to take the inverse sine of this whole thing, right? And the reason why the numbers are different is just because I just simplified these numbers, right? So we went from 4 to 8 and 6 to 3. There's nothing wrong with that. Just make our numbers smaller. You don't have to do that if you don't want to. Just kind of a habit I get myself into. But we take the sine of all of this, right? And that's going to equal e, which is 42 degrees. Now, is 42 degrees our only answer? Well, I told you earlier the answer is no. We actually have two possible triangles that we can draw here. And I'm going to show you how to do that. It's actually kind of neat, right? So if we take our sine of this number, right? Let's say sine of e is 42. Let's think about this. Well, what is sine of 30? What is sine of 42 to begin with? Okay, well, I did it a bunch here, as you can see. Sine of 42 is 0.669. So in other words, 0.67, let's say, right? So in other words, if we were to draw this on a unit circle, and as I will tell you to the point to where you're going to get annoyed by it, reference angles will never go away, right? So if we have a reference angle of 42 degrees here, this point up here on our unit circle where it collides, right, where it intersects, is going to be what, x comma 0.67, right? That's what that value would be here. Well, it's also true that where we have a reference angle here, that sine is going to be the same value, right? Because sine is positive above the x-axis, right? So we know that if a reference angle of 42 degrees is possible, we also know that sine is possibly positive at 138 degrees, right? So 42 degrees, 138 degrees, keep those numbers in your mind. We already solved for the 42, but this 138 does seem like it might be possible, right? So how can we check if the 138 is possible? Well, the first thing we have to do is we have to put it through a little bit of a test, right, to see if it's even possible to begin with. And then once we know it's possible, then we can figure out how to do it exactly. So the first thing we have to do is we're going to draw an altitude down the center of our triangle here. And you'll notice that we know 30, we know 42, right? We know all these other pieces. We're going to draw H right down the middle from the angle that we don't know, right, which is D. And we're going to create an altitude here. Now, what we're trying to find out is we need to know if this 6, right? The side we knew at the beginning was 30. We actually didn't know this 42, right? We didn't know this. So basically, we're trying to see if this ratio here, in other words, if the 30 and the 6 here, if the 6 is greater than the H, right? We need the 6 to be greater than this. Otherwise, it's just one triangle and we don't have another one, right? Okay. So the way we would do that is, well, in order to find H, let's just ignore this 6 for a second. Let's just look at this little triangle we've created, right? Well, we have our opposite, or sorry, our hypotenuse, and we have our opposite. Opposite and hypotenuse is going to give us sine. So if you look at the math down here, right, sine of 30 equals H over 8, right? Opposite over hypotenuse. And then we just solve that, right? So we multiply both sides by 8 to get H by itself. So 8 sine of 30 equals 8 times, well, what's sine of 30? You should know this, right? Sine of 30 is a half. So 8 times 1/2 is 4, which is going to be our value for H, right? So if H is 4, well, is our 6 greater than our H? It is, right? So we are going to actually have another possible angle, right? So let's go and put this 42 back here, right? Okay, so we did that to check to see if we could even possibly have another triangle that could exist. Since 6 is greater than our height, yes, we can. It'll work out. So how can we figure this out? Well, what we're going to do is we're going to take this triangle here, right? We're going to take this triangle here, and what we're going to do is we're going to make an isosceles triangle within it. So in other words, if this was a side length of 6 and an angle of 42, we're going to create another length here that also has a length of 6 and an angle of 42. Right? We create this isosceles triangle, and you'll see it's actually really neat, but you'll see why this is important in a second, right? And now let's try to find what this angle could be, right? Well, if we know that this angle is 30, right? This angle in this corner is 30. So if we know that this angle is 30, we know that this side length is 8, and now we know that this side length is 6, right? Because we'd established that it was isosceles. Well, in order for this to be isosceles, this has to be 42, which means now we can find this, which would form a linear pair, right? So all we would do is 180 minus 42. What's 180 minus 42? 138, right? Do you remember that number from before? 138 is the other number for our reference angle, right? So we know that this angle here, theta, is 138 degrees. All right. Now I want you to look at something that's actually kind of neat. Like, why did we do all this, right? Okay, you made an isosceles triangle. Why? I don't understand why you did that. Well, let's just look at this little triangle here for a second, okay? We have a corner of 30 here, like, right? Angle C is 30. We have a 6, right, on this side, and then we have an 8 on this side, and we're trying to find this angle, right? So 30, 8, 6, and then the angle we're trying to find. Let's go up to the very beginning of the problem, right, when we didn't know that this was 42. We have a 30, an 8, a 6, and an angle we're trying to find, right? So do you see how we've created another triangle that has exactly the same pieces, right? We have a 30 across from a 6, and then we have an 8 across from the angle we don't know. And then when we come down here, after we do all this isosceles triangle stuff, we have a 30 across from a 6, and then an 8 across from the angle we don't know. So you see how we've created a completely different triangle with a completely different angle that also could mathematically justify everything that we've done so far? So that's why we have the ambiguity, is because both are possible, right? This triangle that we've created, this new triangle with E prime, right, our new E, this is also a completely viable triangle based on what we did before, right? And you'd never know that if you just use the law of sines. So when you use the law of sines, and you use the law of sines for side angle, right, this specific thing, you have to do this process to double check and see if it's possible, okay? Which really just kind of comes down to double checking the height and making sure that it works, and then understanding how the reference angle interacts with the angle that you find, 42. But I thought it would be cool to show you like how we can justify creating another triangle. Like, what does this mean? Well, this another triangle does exist, right? I just showed you that. It's actually kind of cool. So that is the ambiguous situation, and it, like I said, it'll only happen if you have side angle situations. All right. So we have one more, law of cosines. And remember when we did the law of sines problem from before, the law of cosines problem is very similar. You're going to plug stuff in, and then you're just going to use your calculator pretty much to solve the whole problem. All right. Now this can get a little bit more complicated if we're solving for the angle, but it's really just a matter of using algebra in a slightly different way, right? So let's find t, which is this length here, okay? So we have triangle TUV, which means we have sides, little t, little u would be 17, and then little v would be 9, right? And now we're going to use our formula. So I went ahead and rewrote the formula here, right, where we have a squared equals b squared plus c squared minus 2bc times the cosine of a. And remember how I told you before, we're going to be able to like choose what this a is and then what this a would have to be? Well, because we're finding length t, we're just going to put that out here. That way we can just solve everything inside here, right, on this half of the equation. So we're going to put a little t here, which means we have to put our big T here. So in other words, we have to use 65 degrees for this, right? And it's ultimately going to come down to what's the angle you know on which one you have to do. So it's actually kind of nice that in this case, right, we can just kind of plug in the one that we need. So let's just go and do that. So we know that we're going to put T over here. So I just rewrote the formula with T's and V's and U's. So it makes sense for what we're using, right? In other words, the V's and the U's, you could switch these. They don't really matter the order of them, right? T squared is going to equal V squared plus U squared minus 2VU times the cosine of our angle T. Plug that stuff in. We'll have T squared equals 9 squared plus 17 squared minus 2 times 9 times 17 times cosine of 65, which was the angle that we had. And from there, we're just going to evaluate. We're going to plug the stuff into a calculator. So I did 9 squared, I did 17 squared, I did 2 times 9 times 17, right? And I got, or negative 2 times 9 times 17, got negative 306. And then you add these together, you get 370. Evaluate this, you get negative 129.32. Then you subtract, and now you get t squared equals this number, which means t, after we take the square root of both sides, equals 15.51. And remember that would equal plus or minus 15.51, but we're referring to a distance, right? And a distance can't be negative, so our answer is simply 15.51. That's it. That's it. That's how you use law of cosines. We used law of sines before, right? We evaluated how to do this kind of ambiguous case, and we kind of discussed like when to use each, and then where it all comes from, right? And that's it. That's 8-2. So I hope you enjoyed this video. I'll see you at 8-3, where we're going to talk about trig identities and then how to add angles together, which is actually kind of neat. So I'll see you there.